So today we have Scott Mcintosh and his presentation on new pathways to bridging the 93 million mile gap. It's an ambitious goal. Scott comes from your midst, as are come the other two candidates also coming from. He got his Bachelor of Science, first class honors in mathematics and physics from University of Glasgow, Scotland. That was back, if I can disclose the year, in 95. And he got his PhD in astrophysics from University of Glasgow, Scotland, too. And you must understand that being a Scot today, Scottish descent, and being here in this audience, in this room, and making a presentation while big things are happening, it's not an easy thing. So I admire Scott for his calmness and his rational approach he has taken today. After he has realized that he actually cannot vote here, but so it makes it easier. Otherwise, I think he would be negotiating for a different date for this. Scott, after getting his PhD in 98, came to NCAR. He was one of our ASP postdoctoral fellows. He went back to the East Coast, not all the way back to Europe, just to the East Coast, to Greenbelt. There was something green about Greenbelt, Maryland, and he went there and became a fellow. But there was something special. He was an external fellow from the European Space Agency at NASA GSFC. He stayed in Greenbelt for a while as a research scientist at the University Space Research Association. Then came back to Boulder as a senior research scientist to Southwest Research Institute. I skipped a few years. That was in 2004. And then in 2007, he came back to HAO as a project scientist too. In 2009, he became scientist 2 on the ladder track. In 2010, scientist 3. And in 2011, he stepped up to be a section head. So he is one of the current section heads in HAO. He has 86 papers in referred journals to his name. He is a person who is passionate about science, and not just about doing scientific research, but also doing outreach, education and outreach, and bringing the science to the community. There are many nice things I can say about Scott and his accomplishments here at NCAR and in the broader community. I would like to point out two things. He is a soccer coach, so that is on I think he's telling them about science while he's teaching them to how to play the game. But also he's stepped up in his role as a scientist to be on the science advisory for DCIST, formerly known as ATSD, or he's been invited to do that. But also he has stepped up as a professional service within the organization and is serving on the NCAR Science Assembly, leading that group. So, without much further ado, I turn it to you, Scott.
Thanks, Vanda. And thanks, everyone, for showing up this afternoon. I know it's been a kind of weary week for a lot of you, and I appreciate your efforts. So, oh, yeah, sure, absolutely. Don't fall asleep. Okay. It's a great pleasure to give this talk and to be standing in a room that the last time I gave a talk in here, I was a mere 24-year-old. It's quite embracing to come back and revisit this room. It hasn't changed a whole lot. Zero. So I'm going to give my ambitiously titled talk, but I hope to convince you all by the end of the 45 to 52 and a half minutes that we can there maybe are new pathways to bridging the 93 million mile gap, or the gap between the sun and the earth. At first, I'm going to offer a little bit of perspective on the problem, then maybe state a little bit about our purpose, and talk about how recent observational work has driven a new look at how the sun-to-earth system works. And then maybe, or no maybe, there will be a discussion probably about 2/3 of the way into how I see HAO's path forward. And then, of course, naturally, we'll sum up and try and bring this whole thing full circle. So there's a very wordy slide. But the principle behind the wordy slide is that we live in the outer atmosphere of our star. That star bathes our planet in photons and particles, and occasionally it bathes us in very nasty things too. As a result of living in that atmosphere, we should really try to understand what that beastie is telling us. Excuse me if I slip occasionally into weird Scottish slang, but I don't have subtitles, I believe. Like terrestrial meteorology, we've divided up the evolution into timescales. Using storm, weather, and climate as categories. But I think, like our terrestrial counterparts, the lines are blurring. This is the kind of concept of seamless prediction, that you can run a weather model in a climate mode or a climate model in a weather mode. And I think, and hopefully what I'm going to show you is that the solar physics is kind of coming that way too. That these kind of semi-artificial short-term and long-term variability stovepipes don't really exist. And in order to understand one, you have to understand the other, and that they coexist. Then, of course, there's this startling realization that we do live 93 million miles away from the sun. And the only way you can figure out what's going on is by catching photons. We can't fly a plane, although it would be very cool. Well, hot, well, cool. Through the sun's outer atmosphere to capture particles in situ. We have to actually catch photons and interpret them. And so that's one of HAO's primary challenges, is to develop the ideas and technology to understand the sun's input, its input to our system. And maybe if you understand them well enough, you can maybe also anticipate changes to that system and how they go down the line. What do I see as our purpose? Well, I would like to see us move forward with a strong desire to undertake world-leading fundamental science while still attacking societally meaningful problems. Let's harness our skill to solve problems that benefit society. Jim and his crew of excellent writers who built the draft strategic plan have come up with two grand challenges for our organisation. And the first one is largely about hazards, space weather in the HAO domain. And the second on climate, the long-term evolution. Pretty impressive things. Maybe 10 years ago they were completely intractable from a solar perspective, but maybe not now. Who knows? I think the path forward is exciting and challenging and engaging, and I think HAO can meet those challenges. Recent observational work that I've pursued with a team of countless colleagues has maybe paved the way to that. It's maybe, and I'll keep using the word maybe, because we don't ever know, because it's a remote sensing science, we can only infer what the sun's inner workings are and how we can trace them. These findings have absorbed me for the last part of the last 2 years, almost to the point of illness. But what have we learned? We've learned through understanding or thinking we can see patterns that determine the decadal variability of the star has given us insight into the centennial variability, weird annual variability, the monthly variability, and possibly even down to discrete events. I'll let you make your mind up for yourself. So we're going to start with decadal variability because that's where our little tale starts. Sunspots, of course, are the perennial marker of the decadal scale of solar variability. We all know that. Sunspots are large concentrations of intensely strong magnetic field. And for the best part of 4 centuries, we've observed their motion across the face of our star. In fact, some of them are so huge you don't even need a telescope to see them. Sunspots, when you collapse the entire disk into one number, when you look at the total number of sunspots in the disk, of course, are quasi-periodic. And the periodicity is 11-ish. And if you're Scottish, that would make you chuckle. because it's non-descriptive. The period, the repetition time of this solar cycle, as it became known, is about 11 years. But when they started to look in detail at the patterns of sunspots on the disk, they noticed this beautiful pattern, this migratory pattern from mid-latitudes to the equator, which then sawtoothed itself back to mid-latitudes and progressed to the equator again, and then repeat, bounce. They call this the butterfly diagram because it looks like a butterfly's wings. Solar physicists are extremely good at calling things the way they see it, or some of them are. Subsequent to that, they also discovered, and excuse my rather crude schematic, that the magnetic field, so here donated by blue and red, blue being negative, red being positive, flipped sign every 22 years on these wings of the butterfly. And you see this beautiful alternating pattern. So they came up with a problem. Oh, sorry. There should be another slide. Oh, no, that's right. So the problem of solar cycles can be encapsulated. What process or processes combine to create the 9 to 14 huge year-long sunspot cycle out of the very regular or the more regular 22-year magnetic polarity cycle? And of course, one of the prevailing theories that's been floating around since the 60s is this idea of a magnetic conveyor belt. That the magnetic field circulates around the sun's interior from so if we draw the radiative zone at the bottom of this top, and here of course is the surface, that there's a large-scale conveyor belt of magnetic flux and plasma flow that contribute to twist and entwine the magnetic field such that sunspots magically appear. This mechanism is called the Babcock-Leighton mechanism. The magnetic field is advected up to the pole, it concentrates, submerges, and then going along this region at the bottom, excuse my hand, it strengthens. The flux tubes that the magnetic flux tubes become buoyant. Buoyancy produces sunspots, et voila. It's maybe not quite that easy. And our little observational tale starts with the humble coronal breakpoint. Here is a picture of the sun's corona taken at emission from approximately 1.5 million degrees. You'll see, like your average teenager, the sun is pockmarked with spots. These tiny little spots are not to be confused with sunspots. These are bright things, not dark things. Well, of course, in the corona, sunspots typically are bright. But small, of the order of a few tens of thousands of kilometers across, blobs of very hot material. They are all over the sun all the time. And of course, here's an example just to show you. Here's an image. Here's an image where all of the bright points on the disk have been actually detected. Being a very naive grad student, when I started this work, I said, oh, well, it takes two polarities to make a bright point, because usually what happens is you have a positive and negative polarity pole, the interconnecting field lines get heated by some magical coronal heating mechanism that nobody knows about, and the result is a bright spot in the atmosphere. Boy, was I in for a big surprise, because when you start to look at these things in detail, here's a magnetogram, and I challenge you to look at this and you see that there's black and white everywhere, salt and pepper. So wherever there's a black and wherever there's a white, when they're in close conjunction, you would expect to see some kind of hot loop. Not the case. I've written 4 papers on these things before I came to that realization. When you come to a broader scope, you realize that these things are actually very well separated in space, and so there's some element of organization. And how do you explore that scale, this organization scale? Well, we came up with a rather crude way of doing it. On the left here is a magnetogram, and on the right is an abstraction of that magnetogram that we call the magnetic range of influence. And this diagnostic is basically measures how far away from me does all the field close. right? So if I have a certain amount of magnetic field here, and with the knowledge that magnetic field always has to balance off to zero somewhere, where's that balance point? What is that balance point with respect to my current location? This is what it looks like, and of course it's in log scale. And you'll see that typically there's big patches of red stuff, and the red stuff has scale lengths of the order of a solar diameter or more. There's a lot of blues and purples. The blues and purples are things down at tens of thousands of kilometers. And as my graduate student at the time noticed something very peculiar about this image, and some of you have heard this story before. But the sun is smattered with a bunch of green things. And being, a Scot, I'm a bit worried about that. I'd rather it be covered in blue things. But really, what were these green things? And when we dug a little bit deeper and compared the two, and what I'm concatenating is what happened in the space of 45 minutes. When we put one map with the other map and figured out that these chronal breakpoints seem to have a preferred location relative to these green things. What are the green things? Those green things mark a scale length of the order of 100 to 200 megameters, or the depth of the convection zone, if you like. They're almost like, if you want to interpret them that way, buoys that are anchored to the bottom of the solar atmosphere, or the convective part of it. And of course, I use the term solar unicorn here because they're a kind of it's a scale that has been hypothesized, and it's been shown fleetingly in observations, but never routinely tracked or diagnosed. And it turns out that our little magnetic range of influence tool that was developed 10 years ago for a completely different purpose is actually useful for tracking and identifying these things. Furthermore, they track with breakpoints. And an old colleague of mine at Goddard, who actually was my boss, set me a task in 2002 to catalogue and track these things. I currently have 200 million of them in a database. Here's what the output of that database looks like. Doesn't look very impressive, does it, for 200 million things? Well, I beg to differ, I guess. And on the breakpoint butterfly diagram, so latitude versus time is on the top. This data set spans all the way from the start of the SOHO era in 1996 to current day, well, not quite current day, with SDO, Solar Dynamics Observatory. On the bottom are these large-scale magnetoconvective, or what we thought were giant cells. We called these things genodes because we didn't know what else to call them. But it seems like a tracer of the magnetic field that's rooted in the deepest parts of the solar ocean. So these two disparate pieces of information tell you a story. They're both connected to one another. So if you combine the information, you get something that kind of looks like a big blurry mess. No. It's not a big blurry mess. You start to see long-lived bands of small-scale magnetic activity, because that's what breakpoints are, that's what genodes are, that trail back in time. In fact, they trail back in time so far that they significantly overlap each other latitudinally. That's interesting. So the challenge I posed next was, can you actually trace those motions? This apparent migration from high to low latitudes. Well, you do that in a very routine way, and actually the first time it was done was in 1980 by Leon Golub, who actually postulated that these chronal breakpoints are something abnormal about them, to use his term, that they seem to be rotating differently from surface structure. Anyone that's familiar with the folklore knows that things that may be rooted deeper in the solar atmosphere experience different rotation rates from things that are anchored near the surface. So by tracking the genode populations and the breakpoint populations as a function of time and latitude, you get something that looks like that. It's pretty cool. But now you can start to appreciate the full extent or some portion of the overlap that's present. And so, here's this, what appear to be bands that belong to cycle 22, bands that belong to solar cycle 23, the bands that belong to the current solar cycle 24, and what one's that? What's the next number in the progression? Oh, 25. Yeah. Maybe hints that cycle 25 had started. These bands take about 19 years, approximately, to get from their high latitude home, where they start to pop up, to the equator. But when they get to the equator and they meet their counterpart, which has an opposite sign in the other hemisphere, they go bye-bye. And that bye-bye is very abrupt. It's on the time scale of a rotation, or maybe 2. So 28 to 56 days. Those bands appear to stop. Part of the problem, I think, with how we've attacked the Solar Variability and the sunspot problem before is that sunspots only map out half of the evolutionary time that we see. And so you don't have enough information to fully constrain the problem. And so if you're constraining it only with sunspots, you're probably going to come up with a different, if your boundary condition's different, you're going to come up with different physics. The hemispheric, what we noticed, and this is the plot here, that the hemispheric sunspot maximum, so if you plot the sunspot number as a function of hemisphere, and it didn't come up very well, there's a red curve and a blue curve and a black curve. The black curve is the total sunspot number. Let's see if this works actually. The red curve is the northern hemisphere, and the blue curve is the southern hemisphere. And if you look at when the northern hemisphere happened, or when it peaked, when activity started turning down, it's when my band of G-nodes and breakpoints actually started migrating towards the equator. This is all largely phenomenological at this point. And some time span later, 2 years, because in our previous map, we see that there is a distinct phase lag between the north and the southern hemisphere. 2 years later, when sunspot maximum happened in the southern hemisphere, coincides with when that band started migrating too. But what that means, or what it implies is, so if you draw polarities on these bands of activity, positive, negative, positive, negative, what is solar minimum? The canonical picture of solar minimum is that there's no field. It's quiet, there's nothing. In this paradigm, it's actually very different. It is actually a time of mass mutual cancellation. Those magnetic bands that live in this domain near the equator all mutually cancel one another until the lower latitude band finally terminates. When that band terminates, sunspots appear akimbo on the remaining band in that hemisphere. The switch on is very abrupt as the termination was. And here's a schematic. And of course, if you can lodge this schematic in your brains, you'll be better off through the rest of the talk. But the idea here is this is now a cartoonized version of the bands, indicating their polarity again, red and blue. They have a high latitude evolution that I kind of won't get into at this point, because it's much more complex and seedy. But the low latitude evolution is where you should focus yourself. And so you can see that at times of solar minimum, you have opposite polarity bands in each hemisphere. But not only that, you also have an opposite polarity band across the equator. So there's a lot of what you would call in meteorological terms telecommunication. This is magnetic telecommunication going on top of any kind of hydro effect. You can, of course, play this game now, where if you know where the termination points are, because that's when sunspots appear abruptly, and you know when the hemispheric sunspot maxima are, because that's when the atmosphere starts to turn down, because you now have interference, you have two oppositely signed flux systems in your hemisphere, you can start to build a picture back in time. And this is just a weird bootstrapping, but what that bootstrapping shows is that the high latitude evolution is very, very regular. Remember earlier that I said that the 22-year solar cycle was very regular. The magnetic polarity cycle was very regular. But the sunspot number was not. It could be 9, it could be 14, and it flips and flops. And that's part of the problem with the intrinsic predictability of it, is that it flips and flops. But the high latitude evolution is phenomenally regular. So what do you have? And while this movie on the right plays, solar minimum in 1996, the contemporary sun. You have 4 bands present. Those bands mutually cancel. So you have positive at high latitudes in the north, negative and positive around the equator, and another negative band at high latitude. When those bands at low latitude cancel, all that remains are the positive and negative band at high latitudes. Sunspots grow with great abandon. As those start to migrate in towards the equator, they begin to connect and talk to one another. The amount of sunspots that it can produce through a buoyant form of evolution goes down. And then you progress with time, those bands migrate towards the equator until you reach the flip side, the mirror image of what was the minimum before. So the mutual cancellation is still there, but it's now reversed in sign. It's kind of pretty. And so what this indicates to you that the sunspot cycle is a consequence of the interaction of these latitudinally interacting bands. Right? It's an interference pattern, if you like. So it's the modulation of these long-lived things gives rise to the sunspot cycle. What have we learned? Well, we learned that the 2 hemispheres of the sun really need to be treated independently. Another thing we've learned is that these activity bands appear at about 55 degrees latitude, like clockwork. We've learned also that they don't migrate, they don't start at the same time. In fact, the profound asymmetry between the northern and southern hemispheres has got something to do with this phase lag that we don't quite understand. The other thing that's very interesting, of course, is that the overlap time is inversely proportional to the strength of the cycle. Longer overlap, more interaction, less spots. The system seems to be driven by the rotation of the radiative zone and probably some global scale magnetohydrodynamics. And I'll get back to that later because I think we're making great strides in that area. There's very strong latitudinal dependence of the patterns that we see. And there's also a very strong feedback between the magnetic field and the migratory flow. So as the field in the band increases, the migratory time goes down. So very strong sunspot cycles have very short evolutionary times. But very weak ones have very long evolutionary times. It's very interesting. Excuse me. So the other thing we've learned is that high latitude evolution seems to play a very critical role in the timekeeping for the whole system, and pose that whether or not there's actually some kind of clock in this regularity that keeps the sun beating. And there's also this possible interface in 3D between a poloidal flow at high latitudes and a toroidal flow that's being driven round by the rotation of the core underneath it. That maybe, and I'm not a dynamo specialist, an interface between a poloidal and a toroidal system is exactly what you need to make a dynamo work. But one of the neat things that we rapidly hedged on was that you have forecast capability almost instantly. And it depends on your ability to draw a straight line. And I'm not very good at that, but my kids are, apparently. And so what this is again under a tracked band tracks, and we've projected them forward. And what we know is, or what we presume is, that when these bands interact at the equator is exactly when the cycle 25 spots should start to appear. And based on these guidelines, that will be sometime late in 2019. So whether or not this is correct, in fact, I should point out that we've successfully predicted when these bands at high latitudes would appear, but never mind. We will be tested, hung, drawn, and quartered based on that prognostication. And of course, that is with the assumption that these bands and their migration stays linear. The record that we have would make you believe that linear is an okay approximation, but it may not be. But we can make a forecast. So again, cycle 22 bands, cycle 23 bands, cycle 24 bands, and cycle 25 bands. And currently, 24 and 25 are both visible. We can track them. We are tracking them. So, decadal scale of solar variability is driven by the sunspot cycle. And that's certainly the most appreciated of them. But there's something we've stumbled on when we were doing this work that's really quite worrying. That there's a modulation in solar activity that we hadn't really taken any care of, and I think it's something to do with the timescale of it. The bigger picture is that solar activity on the whole seems to be on the way down over the last 3 decades. And on the top is the monthly sunspot number. This plot here is the daily flaring rate, so how many flares above a certain value does the sun push out into the heliosphere. Here's a PDF, probability density function, of flare locations, and of course it looks like the butterfly diagram. And of course here's a butterfly diagram from the magnetic fields. But what I want to draw your attention to are a few things. The overall decline in energetics over the last 20 to 30 years. The asymmetric shape of activity that is well known. It's very steep in the ascending phase of the cycle and very shallow in the descending phase. The fact that flare maximum, so here's the sunspot maximum, this black dashed line, the flare maximum follows sunspot maximum by about 2 years. This is called the Gneveshev gap. It's an observational phenomena that nobody could explain. Why is the peak in flares not happening when sunspots are at their peak? Then, of course, there's the hemispheric phase variance, that there is a very strong quasi-annual periodicity in the flaring signal. Very strong. It's a factor of 50 to 100% strong. It's not small. But the two hemispheres are never in phase, very rarely in phase with one another. Last time they were in phase with each other was in 2003. Those flares, these large magnitude flares, cluster both in latitude and in time. So it's not a stochastic process. Something is driving this thing. But what we see are surges of flares. So when you get one, you get another one. And they spatially and temporally coincide with what you see. See these streaks that go off of the low latitudes and migrate? They appear to travel poleward. Those are the instigators. Whatever is driving that pattern is responsible for the variability in the flaring of the star. But it's broader than that. And I'll get into that in a second. But again, we've got to go back to this idea of an overlap. And what is it telling us? In the ascending phase of a cycle, I only have one band in each hemisphere, and so the atmosphere seems to respond linearly. Right? Activity just ramps up because I only have one band in each hemisphere. In the declining phase, after sunspot maximum, I have two. And so the fact that activity falls off in a much more shallow way is because you have interaction going on. It's not just one thing to worry about. These things are interacting with each other. And that interaction isn't just within a hemisphere, it's external. So it's intra and extra hemispheric interactions that you see. And so that offset, the fact that you probably have a sweet spot latitudinally where this band can interact with that band, can easily explain the Gneveshev gap. Why flares and CMEs and all kind of other things peak after sunspot maximum. Because sunspot maximum is just the time when this guy starts. Right? It's not there before that, and so why would... Anyway. Maybe you can see the quasi-annual variability in this mess. The top is CME rate per day now. So not flares, but CMEs. And because it's pretty difficult to disentangle which hemisphere they're from, I kind of can't. And so what you have is in places where the hemispheres are in phase with each other, you get a very strong annual signal. Here, at the start of the last solar cycle. But as the two hemispheres go out of phase, you get this much higher frequency pattern. In fact, this is 150-ish days, which has been reported in a lot of geomagnetic indices for eons. But it's largely because you don't know where your source is, and it's a 3D problem, and you're only sampling one point in space. But the CME rate that we see can modulate by 100% over the course of a year. So the number of CMEs per day can go up by 100% and then fall away again. The same thing can be said for sunspots. The number of sunspots can go up by 50 to 100% over the course of a year and then just fade away again. Challenge someone to explain that. Furthermore, you've got your 100% flare rate increase. So if you're worried about space weather and flares and CMEs, you should be worried about this variability. Maybe much more so than the variability of the decadal scale. But from a radiative standpoint, of course, the sun does it too. Here's the total solar irradiance on the top, provided to me by Greg Kopp. And here's a dial-in. So this is just the last solar cycle. And you can see that the TSI, the solar constant, is certainly not constant on a decadal scale, but it's not constant on an annual scale either. And you can see that there's a 1 watt per square meter modulation per year. Try ringing an atmosphere with that. Who knows what you'll see? So of course this is the TSI. But what happens when you dial down into the spectral bands? Because now we're starting to get this appreciation that the Earth's atmosphere responds to different parts of the solar spectrum in different ways, right? And so when you start to look at the source measurements, you can see the same patterns. So when these have mean subtracted spectra, you can see these clear surges in radiative output of the star go all through the spectrum. In fact, they go all through the spectrum. We have no idea what's going on in the optical and infrared, and that might be the most important one. But the UV modulates by about 5%. The EUV is about 15%, and of course the X-rays, being more sensitive to the corona, are 75 to 100 to 150% modulation. So if you're doing anything that deals with that stuff, you should be aware. I guess thermospheric response to these things is probably very sensitive. Another confusogram. The solar magnetic butterfly diagram, seen now in red and blue for their polarities as we've developed this schematic. The last 3 solar cycles and then the last cycle here. Is it possible to decompose solar surface activity into these 2 epochs? The one being this long-term decadal evolution, which when you subtract it out, leaves you a very clear picture of what's going on interannularly. Can't say that word. So what you're seeing is that the sun, somehow, the processes that form sunspots are being modulated on a quasi-annual basis in each hemisphere. When you drive that flux into the outer atmosphere, it just responds. And it responds by pushing out more photons and more particles. Interesting. One of the big problems I see to forecasting this type of space weather, if you really want to understand what's going on, there may be applications on the Earth that we can tie into. When you look at the Breakpoint butterfly diagram, you know that these bands are not stationary in latitude. They wobble. They meander. Do we know other things, phenomenology in the Earth's atmosphere that meander? Rossby waves, the Gulf Stream, the jet stream. All of these things, subject to rotation, driven by rotation, undergo these large-scale global motions. And in fact, if you make movies of breakpoints on a 3D sphere, this was work that was done by my IRU student last year. It was quite breathtaking. I haven't published it yet, unfortunately. But if you make a Hofmüller diagram, so latitude and longitude versus time, on the right here, there are definite propagating features that would indicate that these deep-rooted magnetic things undergo Rossby-type behavior. Of course, it's a magnetized atmosphere, so they're not technically Rossby waves, but I think there's a great avenue to approach our oceanography colleagues to see how these types of things can form and propagate. Fortunately, we can monitor their progress. Just like the bands, we can actually look at the population density on those bands, and this is what you end up with. very strong periodicities. In fact, the 28-day periodicity you can see also. But all this is trying to figure out how many of these G nodes or breakpoints sit on a band at a particular latitude. You can figure out where you are in the phase of this curve. In principle, you can tell if you're an up or a down. So you know roughly when you're going to go into one of these periods of surge periods. So enhanced storming activity, if you like. So these observations have helped us frame the decadal scale by tracking the activity bands, and then monitoring the number density allows us to look at the quasi-annual scale. What about storms? And I know this seems a little bit like I have a hammer and everything looks like a nail. But I've told you I've been working on this manically for 2 years, right? Not quite manically, but... The most severe solar activity comes from pulses in activity, but often it comes from a particular beast that we call a delta spot or a delta region. And these are very, very anomalous objects. Delta spots predominantly live in the declining phase of solar cycles. Hint. And on the periphery of the butterfly diagram. And this is a plot from Karen Harvey from 1992, which shows the population of correctly oriented active regions on the sun. So those are little stars that you can't distinguish. And incorrectly oriented active regions, which are circles. The circles live on the outside of the butterfly. But those circles are responsible for 90 to 95% of M and X class flares. So a small population, 5% of the spots, responsible for 90+% of the big flares. Where do they live? They live between the bands. They don't live on the bands, they live between the bands. They show mixed characteristics. They're hermaphroditic spots, if you like. They're a mix of one cycle and another cycle, potentially. So by monitoring the evolution of the bands, we can maybe tell you where and when these things actually form. And here's a schematic. And of course, last week we had a huge X-class flare. Well, it's the first one in a while, actually. These zones are just pictorially the mixing zones. So if the high latitude flux merges with this guy, this would be a time when you see irregular active regions in the northern hemisphere or the southern hemisphere. But the time you really need to worry are the ones near the equator. And why? Not only do these bands have the wrong sign, they also have the wrong twist, the wrong helicity. One is left-handed, one is right-handed, and when those two buggers meet, could be pretty ugly. Was Carrington one of those? The low-latitude delta spots are predominantly bad, evil spots. And what about the Centennial scale? Beating my hammer again. We can make this schematic, and all we do here is impose a 22-year clock at high latitudes. We systematically increase the overlap time in the bands, or the migratory time that it takes to get from high to low latitudes. And remember what I told you, the amount of overlap you had dictates how few spots you have. So the longer that time that these bands have overlap, the more they interact with each other, they cancel each other. And so the sunspots would go away. You'd still be cycling, but eventually your clock catches up with you and injects a new system flux, which introduces asymmetry into the system, and boop, you pop back out. And so you'd go from regular 11 years down to 14 to 20 years and back to 11 years in a flash. So, I was to say redefined is a bit tough, but we've kind of reposed what the landscapes of the sunspot cycle are. We've reposed that the interaction of these bands can force activity approaching 11 months, and the surges and the bands can be routinely monitored. The zones of interaction prove ideal places for a complex zoo of things, and violent storm activity. In short, we're making significant observational progress, hopefully with a goal to increase our forecast skill. I'm going to move on. I know I'm running over my time for Q&A. or I'm getting there. But I want to go through what I see as HAO's path forward. First and foremost, to see there's a commitment, needs to be a commitment to excellence. What are our observational frontiers? And I want to develop an understanding based on those observational frontiers to model what we see. And by modeling what we see, I think we can meet NCAR and our community's needs. But in order to do that, we maybe have to think about organising around our mission and around these scientific goals. In order to engage and keep our community, in fact grow our community, we probably also want to engage them. And as a final point, we want to encourage the diversity in HAO to keep that diversity of thought going. HAO, of course, was built in the back of excellent people, and many of those are in the room, and I applaud you and appreciate your work greatly, whether you are admin staff, scientists, IT specialists, you're all phenomenal. And I think you don't get enough credit most of the time for the great work that you do. But I think it's time that HAO realise that a lot of the problems that we have to tackle are not, you can't do one person on their own. We need to work as a team and structure our science such that with a goal of this thing that I call demonstrated success. By demonstrating success on specific goals, you can push forward. You can go to your sponsors and your agencies and say, hey, look, we've got this money, we can do this. I'm going to show you how to do this. Now we need more money for these resources. We match our resources to our tasks and execute. One of the great things, of course, that we're working on in HAO, or our history is built on spectropolarimetric instrumentation. And we're currently building 3 instruments. Well, one's in the design phase, but we have prototypes. Kromagg, the chromospheric magnetograph, the DKIST visible spectropolarimeter, VISP, and then there's Cosmo. A lot of you have heard about Cosmo and seen Cosmo in decadal surveys and NCAR roadmaps. But these things are intrinsic to the future of HAO. They allow us to track the solar cycle, identify magnetic flux regions, and probably trace the impact of those episodes on the morphology and energetics of the sun's outer atmosphere where space weather is born. And they can form a really solid basis for HAO going forward, but based on understanding the sun right now. Understanding what it's telling us right now. It gives me kind of great pleasure to toot Alfred's horn by showing the first light from Kromagg. There's a project that we've conceptualized and he's kind of really run with. And I think through demonstrated success with Kromagg, we can open potential partnerships with the community, with NSO, who are currently moving into town, and towards new ground and space-based initiatives. We've already opened discussions about possibilities with the Global Oscillation Network Group, possibilities on the space station, and possibilities on the next generation solar high-resolution telescope called Solar C. But the profound challenge that has to go hand in hand with those observational frontiers is understanding what we're seeing. And of course, this is a beautiful example by that Yuhong supplied me. Thanks, Yuhong. Of a dynamo model where she doesn't impose many restrictions on the startup. But the demonstrated success with this next generation dynamo model, we can start to understand the blurring of weather and climate, this idea of seamless prediction. Building on that, we can go to smaller scales, and the scales that dominate the structures of the outer solar atmosphere. This isn't playing. Beautiful model that Matthias has just put together that shows salt and pepper fields. It shows the evolution of the solar surface, both magnetically and radiatively, and what's going on underneath, the turbulent mess that's going on underneath. But yet the outer atmosphere seems to organize itself. But this is really a progenitor for where the steps that we would want to take to see how those different scales interact and shape and mold the outer atmosphere of our star. Because why? Because we need to understand where the photons come from. The photons that drive the stratosphere, the photons that drive the Earth atmosphere, are formed in that outer atmosphere in large part. And so we need to move forward and try and illustrate here's a beautiful example from Fang Fang of a jet being formed in the solar atmosphere where we see its emission, 3 different temperatures, and the Doppler structure of this thing. And amazingly, it looks very much like what we see at the highest resolutions on the Sun. And on the right-hand side is built by our colleagues from Oslo. And it shows the emission of the chromosphere, the transition region of the corona, all as one. And so I would challenge HAO staff to come up with a model that goes end to end from the convective process to the radiative environment of the outer atmosphere, because with that model, we can make great, great strides. Well, furthermore, again, keeping this theme of modeling to understand what we see, we need to demonstrate some success with Wacom-X, I believe, and Wacom, and begin to understand both the top-down and the bottom-up forcings for the ionosphere and upper atmosphere, such that we can start to understand the dynamic response of the Earth to inputs from the Sun, and really begin to understand space weather from an atmospheric standpoint. All in all, these modelling efforts can help us construct both spectral and total irradiance inputs for Wacom, for sun climate studies and forecasts. Because remember, we have this forecast capability-ish. We can provide polarization signals needed to validate and understand the measurements of Kromagg, VISP, Cosmo, because we know where all the photons are. We can actually go into the models and pull out what variables contribute what profiles. So that's a huge advance, or potentially, to accompany the instrumentation with the models that back them up and help you interpret the data that you get from them. And finally, investigate the inputs to the ionosphere that drive space weather in the Earth's atmosphere through Wacom-X. I think if we commit to these things and show success, we can actually push forward. So the question is, how would we organize those efforts? And an effort would be form working. One idea I pull off the top of my head is to form working groups derived from a strategic plan that hopefully we will build together, and plan to address, and the working groups would be constructed to address the goals of that plan. That is a couple of benefits. One, that it provides clear feedback to me, to the director, or to Jim, or whoever else on progress on those goals. Furthermore, it allows us to directly map our annual reporting structure and to allocate resources. If one of the groups has been really successful in making headway, why not, if you've got it, help support them, nurture them, bring them along. So regardless in how we organize our efforts, we should really be mindful that demonstrating success is the key to the support of our stakeholders. And by stakeholders, that's both internal and external. Engaging our community, and fortunately, due to bizarre celestial mechanics, we have an incredible opportunity in 2017 to engage and grow and stimulate the public. This total solar eclipse will go from Oregon to South Carolina in the space of 95 minutes. You can't think of a more striking demonstration of the Sun-Earth connection to ingrain it in young minds and others, old minds too. So it's a real opportunity for us to engage the public and actually try to cultivate scientists of the next generation. But again, we need to think about success. To encourage diversity within HAO and keeping its proud heritage of diversity within our own little framework, supporting SOARs and other activities, I would ensure that we have some internal and external advisors who are specialists in the field, because we're not. I'm happy I sat and watched Caroline Brinkworth's presentation the other day and was kind of gobsmacked about how broad and in-depth she knows the situation and realizes that. And I'm sure she doesn't start until October 1st, Jim? Just before that. But she's going to be quite exciting, and I would really look forward to working with her. And I actually would ask her if she has the time to sit on HAO's appointments committee or its high-level strategy committee. Furthermore, I would request that another colleague of mine who I've worked with for the last 5 or 6 years, Dr. Laura Patiklis, at the Berkeley Multiverse, it used to be the Center for Science Education, should be an external advisory committee member because she has of phenomenal input on both science, diversity, and education. And I think we would directly benefit from this because we are kind of responsible for growing our own community in the future, whether we like it or not. We have to take an active role in helping our community be strong. And that starts with nurturing the next generation of scientists. So to sum up, and sorry, apologies, Funda, for eating time. That's their time. I think we can exploit observational insight to develop real, meaningful forecast capabilities. We can use this observationally motivated modelling efforts to refine and nail down that forecast skill. This isn't just unicorns and dreaming. I think it's tangible. I think those breakthroughs allow us to make valuable contributions across NCAR and look to our external partners, particularly from the radiative standpoint and the implementation and execution of the DCIS, the successful execution of DCIS, which is a $300+ million investment by our community into a huge telescope. I think HAO can play a very significant role in that. I think we can be an incubator to grow our own community, and we should be. And I think we have been, but maybe not quite as aggressively as we should have. But finally, we need to work as a team, the whole of HAO, everyone together, to undertake a program of world-leading science, fundamental science that's at the core of the societally meaningful problems that we face and meet the purpose that we're paid for. I'll leave you with a question. Thank you.
Okay, could you turn the light on?
Oh, yeah, sure.
At this point so that we can see well each other? As the last 2 days, I'm looking for the first hands up, and for the consistency, I'm turning to.
Let's see if I can remember what this question is. So, HAO is struggling financially in different ways, and so we are a big mix of base funds and external funds, of which you're the PI on some of those. I'm wondering what you think the right balance is there, and if you were director, would we continue kind of the status quo of everyone to themselves in terms of writing grants, or would there be more direction and coordination in that area?
Well, it's a good question. I think I would certainly like to see a more strategic focus on how we use our money. But I think it would be unrealistic to go to a full base funded support model. Very unrealistic. And so we're in this balance right now, and I don't see how that balance is going to change without demonstrating success on things. You could go to Washington and win more money, but I think only on the back of really successful programs. I would love to grow our core, grow the base. I would love to grow, if grant money is what you've got to live on in the short term, then that's fine. But I would love to grow the base, but I think we can grow the base. I would like to think we can grow the base, but only through demonstrating, using our skill to demonstrate how good we are. We're not just talking a good game, we're going to actually deliver, I hope. If that answers your question. The mix is 50-50 right now. I don't see that changing in the short term.
And what about on the soft money side? Do you think it's right how we're doing, just write a grant, bringing money to pay support or whatever, or would you want there to be more coordinated effort around grant writing?
My perception is that a lot of the grant writing is still strategically focused anyway, even not by design. I think people know roughly where they stand in the organisation, and their sciences are pertinent to that. So I wouldn't actively discourage someone from submitting a proposal on subject they think is really fascinating to them. as long as it stayed somewhat within the purview of what we're meant to be doing.
How do you feel about Scottish independence? No, I'm kidding. I actually have a science. I have a few quick science questions related to your Breakpoint study. Mm-hmm. So, number one, the curve that you showed, it seems to follow the torsional oscillation curve, and so it's
a slide I omitted.
You did. So in the helioseismology, are they seeing the torsional oscillations for cycle 25 yet?
I believe
That's
so.
Just
in the local
the
helioseismology, I believe they do see them. Is that correct, John?
I'll leave that to the speaker.
I believe so. Yes.
Okay. And the other question I have is that you're implying these are very deep-rooted cells, so I know they're short-lived. Is there any way?
They're long-lived.
No, the Breakpoints themselves are short-lived.
Correct.
And you're saying that they're a marker for a mega cell that's deep-rooted. Is there any way for you to track a rotation rate that leads you to believe it has the rotation rate that's seen at the base of the convection zone?
Mm-hmm.
There is. How do you do that?
Well, the kind of quirky thing is that those Breakpoints recur. They recur around the same spot all the time because it's like a locus. And so by tracking the locus, the motion of the locus over however long you want to track it for, you can build up a map of what the rotation rate looks like. In fact, that's one of the things we're thinking about trying to do, is to use the inferred Breakpoint rotation rates as a marker of where they're rooted, if you like, if you understand. I mean, the idea is that surface things are going to rotate at a surface rate. Deep-rooted things and things in the middle are going to have different rates. So it's an area that we've not explored yet, but it's got a lot of potential, I think, for constraining, standard models of solar rotation.
Hi, Scott.
Okay.
How do you identify the idea makers for HAO, externally, internally? How, you put possibly a couple of them up on the screen. How do you identify them?
I think by staying engaged with them. I think by talking and exchanging ideas, you can see where the ideas have been driven from. I honestly believe that kind of casual discussion that engages, it's a collegial thing. It's very odd when it happens, but it's just some other discussion spawns an interaction. And that's when you identify, you see the spark in people, there's a cross-pollination of ideas, that person would be an ideal. I mean, it's pretty easily to spot also from their publication records who's coming up and kind of constantly reinventing themselves and rethinking about the science they may have done 10 years ago. I mean, for example, I just showed you something that I started doing in 2002, published papers on it that I was completely wrong. And I've had to go back and rethink what I was doing. And I think that there's a lot of people, there's an incredible amount of talent inside HAO for doing idea makers. There's a large number, I think. The trick is harnessing them.
Thank you. Hi, Scott.
Hi, Wendy.
What can you do for HAO that the other director candidates cannot?
Oh, that's a loaded question. I think I can bring a lot of creativity and practicality to HAO and really help solidify and ferment the scientific goals. I see myself as a much more action-oriented person. I'm a very much show me, don't tell me kind of person. And so I think I can bring that pragmatic side to helping HAO move forward. I'm not familiar enough with how Stan and Sarah operate. They're both very, very capable. But to say critically how they would address the same thing. But for me, it would be creativity, energy, and an ability to pragmatically look at things and figure out, okay, here's our goal, here's how we're going to get there.
Questions? I know it's the third day in a row.
You've all done very well. Thank you.
So how do you see HAO interacting with the broader community in terms of, do you think the way that we're now operating is a good model in terms of university interactions, interactions with other laboratories? Is there any way you see that perhaps we could get more benefit by operating differently?
That's a great question. Honestly, and you should take a big pat in the back, because I think your section exemplifies how we should operate. I think the community models that you've developed and delivered over the years are a shining example. Unfortunately, the solar science is not mature enough to reach. And I think we have to think, well, we don't have a solar model of the atmosphere and we don't have a solar model of the interior, we may have to think about other ways that the solar side of HAO can contribute to the community to meet your already well-established community input, and that may be through education. I think we have things like CSAC, we have the potential integration with NSO, but I think we need to actively go out and talk to the NSF faculty members that have been hired across the country and bring them into the fold and think about how we interact with them and how we embrace them and try to be a hub for them on this across all of geospace. And that will help HAO in its outreach to its own community. And I think hopefully it'll help us sustain a lot of positive growth between the two. I mean, a lot of our external advisory committee and a lot of our affiliate scientists are already like that. I would love to strategically bring in more affiliate scientists to help achieve these broader goals. But the idea would be a two-way feedback between us and the universities or other organizations. I have no qualms with working with anyone if they want to help us push forward with our goals.
There's a question here.
Forgive me if I really missed it. I didn't see the actual bridge connecting the sun and the Earth because I don't know how these the bright point variations can really affect the propagation and the solar wind and the actual space weather.
Well, I think you make a very good point, but the problem is that it's more of a conceptual bridge than a physical bridge. This isn't the Bifrost that will take you to the dark side or to Valhalla. Is that correct terminology? But it's a bridge nonetheless, and it's a bridge that maybe didn't exist 2 years ago, even the conceptual bridge. And so you have to start somewhere. It's the energetics of the atmosphere. I didn't show you this, but the solar wind and the solar wind mass density also respond with this quasi-annual modulation. So these are all things that need to be factored into models that are all part of the bridge. The bridge is there for all time, whether you're taking a long time to cross it or a short time to cross it, it's there all time. And what I'm saying, I think, is that it's the model. It's a conceptual putting together of things that allow you to form the bridge and start to explore the connections to the Earth system. The Earth's atmosphere to the sun. Our goal is to kind of understand, our goals are to understand the sun and to understand some of the inputs at the Earth side too. But there's a lot of intermediate, high-profile steps that go in the short term, but at least now it's just a conceptual bridge.
How are the bright points related to the coronal heating? Do they take active part? They don't have it.
They're a tiny constituent of the corona.
So it doesn't really contribute to the coronal heating, or directly.
The corona is heated internally within a bright point. That's why they're bright. So coronal heating, the heating of the coronal envelope or the outer atmosphere, is completely unrelated to the process that forms a bright point.
And does it give it clue to?
It may do, but I think there's other avenues to explore that are much more appealing than working on bright points as a marker of coronal heating. There's many other things that I could talk about that I really don't have time for that would show you a much clearer picture of how mass and energy transport into the corona that are not subject to the talk.
Okay. We had a question
Great.
We had a question come in from MLSO yesterday about, and hopefully that person is watching, that's why I'm asking it here. What do you think the right balance is between making observations and building models for HAO?
That's a great question. I think I would like to see 50-50. And I've certainly seen a culture change inside HAO where there's a lot more modeling, and I showed some examples, that models that are designed to explore what we see. And I think there is a shift. 50-50 I think is okay, but I think the idea is that the modeling efforts I would like to see, I'm not saying they have to be, used to explore and understand the things that we're seeing, rather than, let's say, modeling for the sake of modeling. You've got a model that's changed a parameter. I'm not sure that works in that, quite in that modeling to understand what you see framework, if you know what I mean. But 50-50 would be reasonable. I think you lose a balance in the ability to interpret the photons properly if you go all observational. And if you go all modeling, you've got no observations. So it's an observationally driven science, whichever way you look at it. And the models help you join the physical dots. It's a join the dot puzzle with no numbers.
So for consistency, since we are talking about observations, I will ask the same question I asked yesterday. Budgetary realities aside, if you could tap into whatever resources are available, again, I'm allowing you to dream big. What would be your observational system of the present or the future to help you move things forward and build not just a conceptual bridge, but a more solid bridge?
Well, I think you'd start with the finishing off or completing the Cosmo development. There's a real clamour for coronal field measurements. It's kind of a missing link in space weather to constrain space weather models. The three different components of Cosmo build together to build a physical picture for the heliosphere. So I'd start there, but the really crucial piece of infrastructure that needs to go with that commitment of resources is the ability to understand what you're seeing. And I don't think you can realistically build such a telescope. And it's the same, I'd make the same charge to NSO. They built the DKIST. We need to help them. And the same thing that I'm talking about with respect to understanding where the photons come from, where they're formed in a model framework, would help you understand not only Cosmo, but help you understand the DKIST data too. And so it all hinges on this ability to not only capture the photons, but to interpret them to within your knowledge of the physics. Michael.
May I ask for a microphone to be passed back? Maybe Brent a bit.
So, since this is the last of these presentations, I feel compelled to remark that I was sitting through these three talks and realized that pretty much exactly 20 years ago I gave a presentation in this room as a candidate for the HAO director. And in my talk I announced that what I would like to establish at HAO was a substantial leading effort in MHD modeling that would complement the precision polarimetric measurements that HAO had pioneered or was in the process of pioneering. And the other piece that I announced in my presentation that I felt was necessary was to lay the foundation of a new generation of scientists in HAO, and part of this new generation is talking as candidates here. If you look forward 20 years, where would you see HAO at that time?
Great question, and thank you for the great question. Honestly, I'd like to see HAO being a place in the community where people feel home. They feel that they're part of our family. They feel that they're involved in HAO. And I'm not just talking about people that work here. I'm talking about our whole community, that we be a central hub. That's what I would love to see. Scientifically, I can't predict what's in the future. You were very bold. You've called out largely what I'm still talking about. MHD simulations to understand complex line profile formation. We're still not there. This is 20 years later. Maybe that's what we say, is that, well, we're going to build these phenomenal instruments, but by Jove, we're going to understand the photons that come from them. But really, honestly, I want our community to feel invested in HAO, because I think that's how HAO succeeds and grows. And it may well be that delivering on such a modelling framework to help them understand their photons too, we can do that as just one activity.
And the second part, how do you want to get going again with young scientists?
Absolutely. I think we need to bring some fresh young blood and cultivate that young blood inside HAO. And I think we've got some phenomenally talented project scientists in our midst. And I would like to help them establish their careers within NCAR and help us push forward. And who knows, 20 years from now, maybe one of them standing in my spot.
On that note, I just thank Scott.